Okay, a couple more examples using Newton's second law in both its linear and rotational formats. Here's a really common problem. We have some sort of a ceiling, and we have some sort of shape hanging from the ceiling. Let's make it a pulley that's a disc again. We wrap a rope around this disc, and we hang from this disc a weight. Okay, so this is going to be mass of M. This pulley is going to have a mass of capital M and a radius of R. And if we drop this weight, the pulley is going to unspool as this thing falls. But it's not going to fall with an acceleration equal to g, because it's not free to fall. There is still some tension here because it's got to drag this or spin this pulley along with it. So let's figure out what the heck is going on. Once again, we're going to have a free body diagram for the hanging weight, and we're going to have an extended body diagram for the pulley. Now, on the free body diagram, we know that F net equals M times A, and on the extended body diagram, we know that the sum of all the torques equals I times alpha. This is a net right here. Okay, good. Now, the net force is mg downwards minus g upwards, and that's going to equal ma. Here, the only torque is the torque from this thing here, this tension. So the tension acting at a distance r is going to equal 1/2 capital M r squared, and I'm going to replace alpha with a divided by r. Once again, the magic of the r's. This r down here cancels the square. This r and this r cancel, meaning the tension is 1/2 of the mass of the pulley times A, and that's probably good enough to just put it in here. So little m times g minus 1/2 of big M times A equals little m times A. Collecting terms, this goes over to the other side, and we're going to have little m times g equals little m plus big M over 2 times A. Thus, A for this system is going to be little m over little m plus big M over 2 all times g. Fun times. And of course, if they ask us for the tension, we can just put that back in. If they gave us numbers, we could put those in. But we're going to have an acceleration that's less than g because the denominator is bigger by half the mass of the pulley. I once came up with this idea before CGI was a really big idea. One of the things that was hard to film was people falling off of buildings and stuff. And what I wanted to do was have a hidden cylinder on the top of the building, and wrapped around it was a very small steel cable, and then over the edge of the building it would go over a pulley, and then a stunt person would hang from it. And if the mass of the stunt person and the mass of the cylinder were chosen correctly, you could get the acceleration of the stunt person to be g divided by 10. That means only about 1 meter per second squared. And for a 5-story building, you don't have to have a bag or anything to catch the person because they really won't be going that fast by the time they hit the ground, that a properly trained stunt person will be able to handle a landing at that speed. And then all you have to do is speed up the film by a factor of 10, and it will look exactly right. Now, the only thing that the stunt person has to do is the stunt person has to make sure they don't move their arms and legs quickly, because when you play the film back at 10 times speed, the motion of your arms and legs will be 10 times faster, and you'll look like some sort of hyperactive, I don't know, whatever. Anyway, this would be a great way to be able to film somebody falling all the way off, and all you'd have to do is somehow digitally remove the cable. And so turns out, though, that that's not really necessary. They have systems like this, and then, of course, CGI makes it so that you don't have to do that. Okay, there's one more variant on this I wanted to cover. Okay, that's good. Just throw the pens everywhere, Harmon. That's nice. Oh, there we go. And that is an interesting variant on this is the idea of having the rope wound around the spool, but then attached to the roof, and you just drop the spool. Now, that means that the spool, the disc, is providing the weight, and it's also providing the rotational inertia. Whereas this thing will fall down like a yo-yo. It'll be in this position and as it accelerates down. And what will the acceleration of this thing be? Now that's really interesting. You can simulate this if you'd like to. Get yourself a roll of toilet paper, if you can still afford toilet paper, and hang on to the end and drop it. And you will see that it doesn't fall as quickly as if you were to drop another roll next to it. Cappuccino. All right. So this one is kind of interesting because, we could pick a lot of different axes of rotation, but I think you really want to pick the axis of rotation that is the center of the mass of the object. So we need a free body diagram where m times g and t is going on here. And then we need an extended body diagram where t is going on here. And it's the same mass that's in both of these things. So this is kind of fun. But we do the same steps. We do Newton's second law, F net equals m times a. And over here, we do net torque equals I times alpha. Okay. We know that it's going to fall down this way, and we know that this thing is going to unroll this way, so those are going to be the positive directions. So m times g minus t equals m times a. And over here, t times r equals 1/2 m r squared, and then the quantity a over r, putting in my rolling without slipping. As long as this rope does not slip along the outside edge, we're in good shape. And the magical cancellation of r continues. Put that in over here, and you're going to wind up with m times g minus 1/2 m times a equals m times a. This goes to the other side, and we have m times g equals 3/2 m times a. The m's cancel, and we wind up with the acceleration being 2/3 g. As long as the mass is also the thing doing the rotating, and as long as it's a cylinder, then we're going to wind up with an acceleration that's 2/3 of g. That's kind of fun, and I thought you might enjoy that.